Each of the following equations determines a plane in space. Do the planes intersect? If so, describe their intersection. So here we have this beautiful linear system of three equations, and these equations are homogeneous equations. If you really wanted to confirm that to yourself, we could convert this to the equivalent matrix equation. We can see that our coefficient matrix going down the first column is 1, 2, -1. We then have 2, 1, 1, and our third column is 3, 3, 0, multiplied by the vector in R3, so the vector with three entries, x sub 1, x sub 2, x sub 3, and this is equal to that constant vector, 0, 0, 0, so the zero vector. So again, this is really driving home to us that this is a homogeneous equation. Matrix A times vector x equals the zero vector. So we're being asked here to determine if these planes intersect. So we need to solve for the solution set or describe our solution set. So how are we going to do this? Well, to get us started, we're going to need to row reduce the augmented matrix. So we want to row reduce matrix A augmented with the zero vector to row reduced echelon form. And we'll pause for a cause when we hit echelon form, if it exists, to see if it's going to be a trivial solution or a non-trivial solution. So here we go. We have the augmented matrix 1, 2, -1, 2, 1, 1, 3, 3, 0. And again, we are augmenting this with the zero vector. So, to row reduce this, we start with our first pivot position, and we want to use this pivot to eliminate the entries below it. So we need two steps here. The first thing we want to do is multiply the first row by -2 and add this to the second row to attain the new and reduced second row. We'll then go ahead and simply add the first row to the third row to attain the new and reduced third row. So here we go. So with this equivalent row equivalent matrix, the first row remains as it is. 1, 2, 3, 0. So then we have -2 plus 2 to give us 0. We have -4 plus 1 for -3. We have -6 plus 3 for -3. And of course, 0 plus 0 is 0. Now moving to our third row, we're going to have 1, let's use a different color here. We have 1 minus 1, which gives us 0. We have 2 plus 1 is 3. We have 3 plus 0 is 3. And last but not least, of course, 0 plus 0 is 0. So our first column is all set, and we'll move to our second pivot position. And so we want to use this pivot to eliminate the entry below it. And we lucked out here. All we need to do is take the second row and add this to the third row to attain the new and reduced third row. So here we go. In this case, the first two rows of our augmented matrix remain as they are. We have 1, 2, 3, 0. We have 0, -3, -3, 0. And then we're going to have -3 plus 3 gives us 0. And I skipped my first column. It should be 0 plus 0 is, of course, 0. Then -3 plus 3 is 0. The third column, we have -3 plus 3 is 0. And of course, 0 plus 0 gives us 0. Woohoo! So wait a minute. We got to pause for a cause here. We can make some great observations about this linear system or this homogeneous system. Notice here that we have echelon form. So we know at least one solution exists. But also notice that your third pivot position is 0. So this is also letting us know that x sub 3 is a free variable. Now, because the left-hand side and the right-hand side are both equal to 0 here, this is not a contradiction. It just implies that x sub 3 is free. So, now let's go ahead and continue row reducing this augmented matrix to its row reduced echelon form. So again, going back to our second pivot position here, let's start by scaling the second row by a factor of -1/3, which gives us the equivalent augmented matrix 1, 2, 3, 0. We'll have 0, 1, 1, 0, and our third row is still all zeros. And one more step to go. We're going to again take this second pivot position and use it to eliminate the entry above it. So we'll do -2 times the second row plus the first row to attain the new and reduced first row. And let's give ourselves plenty of room. So here we are left with the equivalent augmented matrix. We're going to have 0 plus 1 is 1. We have -2 plus 2 gives us 0. We have -2 plus 3 is 1. And then, of course, 0 plus 0 is 0. And our second and third row remain as they are. So we have attained row-reduced echelon form, woohoo, and we're ready to start describing our solution. We want to go ahead at this point, again, now that we have attained row-reduced echelon form, we want to take this system and describe the basic variables or rewrite the basic variables in terms of those free variables. So just rewriting this system as it is, the first row reads that x sub 1 plus x sub 3 is equal to 0. The second row reads that x sub 2 plus x sub 3 is equal to 0. So taking this and solving for our basic variables, aka x sub 1 and x sub 2, we have x sub 1 is equal to minus x sub 3, your free variable. We have that x sub 2 is also equal to minus x sub 3, our free variable. And then we'll also indicate here that x sub 3 is free. It's any real number our little hearts desire. So now that we have described the basic variables in terms of the free variable x sub 3, we want to go ahead now and write the general solution vector x as a parametric vector. So let's go ahead and write that general solution. So we have the general solution. This is vector x in R3. So since we know the general solution vector, vector x, is in R3, it is a vector with 3 entries, as we indicated at the very beginning, when we rewrote our system in the matrix equation form. So using what we found above, we know that x sub 1 is equal to minus x sub 3, that x sub 2 is also equal to minus x sub 3, and x sub 3 is free, so it is just itself. Now we want to take this one step further. We should actually also include here that x sub 3 is free. It is a scalar value. So this is great thus far, but we want to describe the solution set geometrically. So we need to decompose our solution vector into a linear combination of a constant vector times the parameter x sub 3. So we are decomposing vector x, and we can say our beautiful final answer here, vector x, is equal to the parameter x sub 3, the free variable, multiplied by the constant vector, the scalar valued vector, -1, -1, 1. And this is such that x sub 3 is free. It's a real number. So here is the solution set in its parametric vector form. So this is the first part of our solution. We have found the parametric vector representation of our general solution vector x, but we want to take this one step further and describe our solution set. So we want to describe the solution set geometrically. And if you see it, by all means, go for it. But let's break this down real quick to really understand what's going on. So looking at our parametric vector, we can say that vector x is the set of all scalar multiples of our scalar valued vector. So vector x is the set of all scalar multiples, or all linear combinations of the vector, the constant vector, -1, -1, 1. So the set of all scalar multiples of this vector. Let's think about what this actually looks like in space. So we have the z-axis, your x-axis, and the y-axis. And so your x-axis is x sub 1, the y-axis is x sub 2, and our z-axis is x sub 3. And so we want to start here by plotting our scalar valued vector, -1, -1, 1. So from the origin, we're moving 1 unit in the negative x direction. We're going to move 1 unit in the negative x sub 2 direction, or y direction, and then we want to move up 1 unit in the positive z direction, or x sub 3 direction. So the position vector comes from the origin to that point, and so here is the vector -1, -1, 1. Now, our solution set, again, is the set of all scalar multiples of this vector, -1, -1, 1. So, meaning all of the scalar multiples moving in a positive direction, continuing forever and always, and all of the scalar multiples moving in the negative direction. So remember, this is also known as the span of that vector, -1, -1, 1. And what does this span look like? A line! So we can say that our solution set, or the intersection of these three planes that we started with, is the line in 3 dimensions that's passing through the origin and pointing in the direction of the constant vector, -1, -1, 1. So our geometric interpretation, let's make sure we can still see our parametric vector. So we can say that, therefore, the intersection of these 3 planes, so the intersection of these 3 planes, the 3 planes that we started with, is the line in space, or the line in R3, passing through the origin, aka the 0 vector in R3, in the direction, or parallel to, the constant vector. So in the direction of the vector -1, -1, 1. So the intersection of the 3 planes in our homogeneous equation is the line in R3 passing through the origin in the direction of the scalar valued vector -1, -1, 1. And this geometric interpretation is great because we can see here the trivial solution of our homogeneous equation. So the 0 vector is just one of the infinitely many solutions to this homogeneous equation. So if we wanted, we can even indicate here that this line in space passing through the origin and in the direction of that scalar valued vector is the solution set to the given homogeneous equation, matrix A times vector x equals the 0 vector. This is the line containing all of those infinitely many solutions.